Hello and welcome to VTS 2021. My name is Debarshi Chatterjee. I'm a senior ASIC verification engineer at NVIDIA Corporation. The primary author of this paper is Siddhant Doli, and it's also co-authored by a couple of my colleagues, Eric Hale and Saad Godil at NVIDIA Corporation. In May of last year, NVIDIA announced their brand new GPU based on the Ampere architecture. When it was announced, Ampere showed an impressive performance boost of 20x for AI and ML type application over previous generation GPUs. While it's well known that we use GPUs for boosting the performance of artificial intelligence and ML type applications, we also use AI and ML for various flows for design and verification within NVIDIA. And in this presentation, I'm going to discuss about one such verification use case of AI and ML for boosting the coverage of stalling regressions. In recent times, stalling virtual channels and interfaces are becoming increasingly more important to find timing critical corner case bugs. In many cases, stalling introduces or exposes deadlock scenarios. It also exposes ordering rule violations, credit underflow and overflow issues, and sometimes filling up these internal structures which are designed to not become full because of performance reasons. If we fill them up and cause back pressure, it often reveals other corner case bugs. So how can we stall? There are various mechanisms of stalling, and one of them is using BFMs or bus functional models to delay credits or oftentimes responses from the BFMs could be delay causing stalls. We could also use shims in between RTLs to cause VC throttling. And the third form of stalling, which we're going to focus in today's presentation more, is Fifo or pipe stalling, where the Fifos and pipes are stalled based on a custom stalling infrastructure which is inserted within each Fifo module. We will now take a look at how Fifo stalling works in our verification framework. And before I explain that, let me just go over what Fifo is. Fifos are first in, first out components which are used very extensively in hardware design for storage purposes. On the right side of the Fifo, there could be signals like clock, valid, and data. Whenever the transmitter wants to transmit packets into the Fifo, it will assert the valid. And if there's space inside the Fifo will let the transmitter know by asserting the ready. When there is no space, the Fifo will again let the transmitter know by deasserting the ready. So if the transmitter wants to transmit a packet, it asserts the valid. If its space is available, ready is asserted, and when valid and ready are asserted at the same time, the packet is said to have transmitted. In general, the Fifo's depth is designed in a way that it doesn't get full that often, and this is done in order to prevent stalls in functional pipelines. And so such back pressure is not generally seen. So what we do is that we artificially introduce such stalls in the Fifo by introducing a custom logic within the Fifo, which will be explained in this FSM on the right. So in this special mode of when this kind of artificial stalling is enabled, what happens is when the valid comes in, that the Fifo is in the start state. So when the valid comes in, and the Fifo then generates a random number between 0 and 100, and if that number is less than the stall probability, then it will move to the pre-stall state. So stall probability is one of the stall parameter registers which the user can program within the Fifo. Each Fifo has these three stall parameter registers: stall probability and the min and max duration of the stall. So when the valid comes in, it generates a random number between 100. If it's less than stall probability, it will move to pre-stall state. At this state also, the Fifo is not stalled. In the pre-stall state, what the Fifo does is that it generates a random number again between the min and max duration of the stall and puts that number in the register cycle left. And then in the next cycle, from the pre-stall, it moves to the stall state. In the stall state, the FIFO deasserts the ready, that's the artificial stalling, and then it counts down every cycle, the cycles left. As long as the cycles left is greater than 0, it will loop in this state, and when it becomes 0, it will go back to the start state and release the back pressure. This is exactly what's shown in this diagram, where we have the FIFO behavior with the stall probability programmed as 100 and min max duration programmed to be between 5 and 10. So it randomly generated a number 8 and counted down and had the stall asserted for 8 cycles. In the previous slide, we saw how the selection of stall parameter registers in a FIFO affect the stalling behavior of the FIFO. If there are n such FIFOs in the design, then there are 3n such registers. And in this slide, we're going to discuss how the selection of those 3n values affect the stalling behavior of a test. And we're going to argue that a random selection of those 3n values is suboptimal. So before we select all these 3n numbers of stall parameter registers, we need to decide how many FIFOs we would want to stall in the test. And if that number is too low, then it's possible that the stimulus might not cross stalled FIFO and there's no stall in the test. If it's too high, then there might be too much cross interaction. For instance, if you want to get a FIFO full condition of a downstream FIFO and there's a simultaneous upstream stall, that might be detrimental for that. So empirically, we found that sparse stall that's randomly stalling 1 to 2% of FIFOs in a test yield decent results. But how do we decide the stall probability for a particular FIFO and for n FIFOs? And if we do random selection, it's likely that we'll select a high probability stall probability value for a FIFO that shows too much activity in a test. And if we do that, then that FIFO will get stalled every time a valid comes in. Ideally, for these kind of FIFOs, we would want to have a stall which would hold for a long time, and not at every valid. We don't want to stall for a high busy FIFO. And again, for random stalling, we might encounter a low stall probability on a FIFO, which in a particular test show low activity, and that might result in a situation where we didn't stall anything at all. And selection of stall duration is also very important. If you want to achieve FIFO full condition, then the stall duration should be should be long enough so that that based on the arrival rate and the depth of the FIFO, it fills up the FIFO. So stall duration is if you want to achieve FIFO full condition, it is a function of the arrival rate and the depth. Again, for us, there's no way to know that ahead of time because the tests are random. And so random selection basically doesn't account for those information. Also, if the FIFO, if the stall duration is randomly selected too high for FIFOs that are sitting at the input of the DUT, then it just back pressures the BFM, doesn't do anything interesting. On the other hand, FIFOs deep in the design, if they're stall high, then it can generate interesting back pressure. So the point is, if we know a lot of these things, like what is the activity, arrival rate, or activity on a particular FIFO in a particular test, and what is the depth of the FIFO, what is the arrival rate, and how the FIFO is located in the FIFO tree, then we might be able to make better decision of the selection of the stall probability and other stall parameter registers. But random selection doesn't have that information, and so is suboptimal in selecting for coverage perspective. So the selection of stall parameters randomly is not just suboptimal, but also it is almost impossible to explore the entire state space of the stall parameter registers. And this is because there are 3n such registers, and even if they could take 2 values, that would result in 2 to the power 3n combinations. And with n of the order of 100,000 or 10,000 to 100,000, depending on the test bench, that number of combinations is impossible to explore practically. So we should select stall parameter registers in a way to meet our objective, and this objective is coverage condition. So for stalling regressions, we are aimed to hit coverage conditions such as FIFO full coverage condition, RAM full, and complex coverage conditions, which involve across of these full coverage conditions with timing events such as eviction, invalidation, and various other coverage conditions. Now, this coverage objective is a complex function of the FIFO topology, test stimulus dot configuration, and the stall parameter registers. And that is no known closed form. And so we cannot really use conventional optimization techniques to figure out which value of stall parameter registers which would easily or maximize the coverage objective. So what are the options here? The option is one of the options is directed testing. If a coverage condition is too hard to hit, we could manually go and write some directed test, but as a general strategy, it's too expensive to hit all coverage conditions. We usually use this as a backup option when random testing does not hit, but we would want almost everything to be hit with pure random testing. But the problem with pure random testing is that it's too slow for coverage closure. And so what we're suggesting in this paper is the use of an evolutionary computation technique to select the stall parameters. And why does this work intuitively is that we know that there exists that this coverage there exists an underlying function which maps the relationship of the test stimulus dot configuration stall parameters to a coverage number. Although we don't know that function, what we could do is that we could keep the seed of a test same and run this same set test seed, which will have the same dot configuration and same stimulus pattern with multiple stall parameter registers. And we could see how that affects the coverage, learn from that, and use evolutionary computation technique to explore the state space of the stall parameter register to maximize the coverage objective. In this work, we're going to use genetic algorithms to select stall parameter registers. A genetic algorithm is a heuristic inspired by evolutionary biology. In evolution, we start with a random population, and the population with and the members in the population with higher fitness values is selected into a mating pool, and those members get the chance to produce offsprings, and the offsprings become the next population. So you calculate the fitness of the offsprings, and then from that generates the new population, and this process is repeated. And by repeating this process over a period of time, if the population evolves into a higher fitness population. And in our work, we use elitist genetic algorithm, which means some of the highest fitness individuals are allowed to move from generation to generation. Let's see how we can map the problem at hand to a standard genetic algorithm. In a standard genetic algorithm, we have a population of members, and in this case, we have a population of tests. So each member in the population will have a genotype, and in this case, each test in the population will have a genotype. So the genotype of the test will be the test seed and the stall parameter registers. And in the standard GA, each population member has a fitness, and in this case, each test has a fitness, and the fitness is nothing but the weighted sum of the coverage objectives that the test can hit. To generate the random population for starting off the GA, we have to, in this problem, create a population which has multiple copies of the same test seed with different random stall parameter register. So we will have, let's say, a test seed X1 with different stall parameter register, test seed X2 with different stall parameter registers, and all of them will be in the initial pool. So that's a special consideration in this case for this problem. And the reason is for doing that is we only allow crossovers to happen between members having the same test seed. And again, that requirement comes from the fact that we want to keep the test seed same so that the dot configuration and the test stimulus is same, and we only explore the state space of the stall parameter register as a function to maximize the coverage or the fitness. So coming back to the fitness here, so fitness is defined as a weighted sum of the coverage metrics. The thing, again, for this problem, we have to make sure that none of the coverage metric is like has a jump. So for instance, a common case is FIFO full condition, which could be either a 0 or a 1. We have to transform that kind of a 0-1 type of coverage into a smooth coverage or a continuous metric, so that we could define, instead of doing FIFO full or not full, we can define a metric FIFO occupancy over the FIFO depth, in which case that metric could be somewhere between 0 and 1. That can become one of our CIs. The reason we need to do this is because we have to define fitness as a continuous objective, so that when we explore the state space of the stall parameter register, we know how it is doing, and so that the coverage can actually converge to a higher value of fitness. Other than that, the rest is pretty much standard. We use standard selection scheme, which is fitness proportionate selection, standard crossover operators, and just the legality has to be ensured, so that when crossing over, the min and max is greater than min, and that's pretty much it. So we applied the GA stall on 2 different test benches across various objectives and captured the data in this the bar graph. So each of these represent a coverage objective in a particular test bench, and the green line represents the coverage boost from the GA stall normalized over simulation time, and the red one is the random stall. So across various test benches and various coverage objectives, we found that the GA stall boosted the coverage for the same amount of simulation time. And the average boost for a particular test bench A was seen to be 163%, and for the other one, the boost was 88%. So although in previous slide we saw how GA stall was impressively able to boost the coverage results for various coverage metric across different test benches, we were only running the genetic algorithm for only 100 iterations. And so we felt that if we were able to run more longer, and then we would probably be able to improve it further. But in doing so, we ran into some scalability challenges, which is what we're going to discuss in this slide. So if you look at one iteration of the genetic algorithm, the main runtime is running the tests. So we need to run the tests to evaluate the coverage, and then evaluate the fitness. And if there are X members in the population and that X is below the farm capacity, then we can parallelize all those X runs. And within 5 hours, we can complete all those X tests. Within half an hour, we can complete all those X tests. And then eventually, if for 100 iterations would roughly take that half an hour times 100, and that's about 50 hours. So within 50 hours of time, we could do 100 iterations. But what if you want to do 1,000 iterations? That would take 500 hours or 20 days. And that is where the scalability becomes a problem. And that scalability bottlenecks comes from the fact that we are running the tests themselves to evaluate the fitness. So in the subsequent slide, we're going to discuss how we can create a deep learning based model, create a prediction of the coverage metrics without actually running the test. So to overcome the scalability issue, we introduce something called GStall, where we replace the DUT, or the design under test, with a multi-layer perceptron model, and the MLP will give us a prediction of the coverage. So we use a 5-layer MLP, and to train the MLP, we generate 30K tests. These are split into test and validation data sets. And so to generate these test data, for instance, we had to run 30,000 tests, 1,000 in parallel. So it took us 15 hours of runtime to generate that. And training the model is not that expensive, but once the model is trained, um, generating the fitness evaluation almost takes 1 second. And so now, as you can see, the whole process becomes much faster with deep stall. So now the question was, with the deep learning based model to predict the fitness, does it perform better or worse? We know we improve the runtime, but we might lose some accuracy in terms of prediction. So in the next slide, we'll see how the deep stall based prediction works when used within the genetic algorithm. So here are some of the charts which shows the results of the training of the deep learning based model on the training data set and the test data set. So in this chart, the orange ones dots are the predicted values of fitnesses, and the blue ones are the actual value of fitnesses and on the training data set. And no surprises, they were very close to each other. And this is the same thing for the test data set. In this case, we saw some divergence of course, from of the predicted value from the actual value, but it tracked very closely, and they were within an envelope, which gave us some confidence that the DL-based prediction is actually giving us good results. So in this slide, we finally compare the results of random stall, GA stall, and deep stall on a particular coverage objective, which has a maximum value of 128. With random stall, we found that we were able to hit the coverage value of 90. With GA stall, we were able to boost that coverage to 113 by incurring some additional wall clock time of 50 hours for the genetic algorithm. In deep stall, we replaced the actual running of the test on the DUT for fitness evaluation with a deep learning based model. And so by doing so, we were able to run the genetic algorithm 10x longer and converge more, which caused the fitness coverage to be boosted further to 126 while incurring a very little cost in terms of generating and training the DL model. So overall, I would say that this shows some promising results in the use of a DL-based genetic algorithm for improving the coverage objectives of a stalling regression. In conclusion, I would like to share some of the learnings from this work. And what I found out is that that while we are creating a fitness function, which is the weighted sum of all the coverage, it's possible that certain coverage metrics are such that you have to sacrifice other coverage metrics to achieve that. And so it's possible that multiple sets of stall parameter registers might be useful, where one set might be good to boost one coverage, the other set might be good to boost other coverage. And so ideally, we would like to have a Pareto optimal set of coverage vector instead of combining them into a single objective. And there exists a lot of literature on multi-objective evolutionary algorithm. So as a future work, we would want to explore that area and also see how the DL model is able to efficiently predict multiple objectives. Thank you for listening to my presentation.